Okie dokie. So, ooh, I actually get a chair today, maybe? And it spins, that'll be. All right, nice. So, I think there was some miscommunication on my end, so I apologize for that. The quiz is online, but I think I neglected, we're not doing it in here. I'm sorry, I should have been specific with that. Like I said, the whole point of quizzes is not to sit here and stress you guys out while we're in class and that kind of thing. I'll find different ways of doing that, okay? So, so the quiz should be open up. I think it opens at 11 and then it won't be due until like tomorrow night, basically is what it is. So you guys should have plenty of time to do it. It's there just as practice. The questions are about as straightforward as you can get, I hope. And like I said, it's there for you guys to say, hey, if I'm struggling with this now, I need to get that issue resolved before we get to the exam, right? So hopefully you guys find some time to just get that knocked out. It's only like 5 questions or so. The one thing, the last question on the quiz, I'm going to ask you guys to upload your work, right? So snap a photo of your work, upload it there. That's what's going to be the really important thing for you guys when you get through to the exam and all that kind of stuff. So write out your work, show it to me, that kind of thing. Sound fair? Other than that, it's just unit conversions. And 2 of them come directly from the book, right? Sound good? Cool. Yeah?
Is there a time limit for the quiz?
No. Yeah, nothing like that. Yeah.
Is it open book?
Yeah, sure. Go for it. Sounds good. Yep. Good? All right, so everybody should get a easy 10 out of 10 on this first quiz, yes? All right, that's what I'm expecting. Okay, cool. Other than that, last time we were walking through the periodic table and we had gotten to one of the big topics where I subtly hinted that this is usually what shows up on exams or future quizzes. This stuff isn't on the quiz, right? The quiz is basically about chapter 1 and the stuff we talked about in there, right? So we talked about this elemental composition, not elemental composition, the isotopic composition, right? And we talked about how we can calculate that and how to calculate the atomic mass and what the different numbers on the periodic table tell us, okay? So we walked through a couple of practice problems with those. We walked through the math and kind of hopefully you guys spend a little bit of time just looking over that before we came to class today, right? So one of these important topics, like I said, guarantee is going to show up on the exam, right? So make sure you guys are comfortable doing some of this math. Sound good? Cool. Other than that, today we're going to get to the next big, let's say, stumbling block here, which is going to be naming. All right, so we're going to learn how to name some things. We're going to learn how to put some things together, and that's going to be one of these other big topics that come on the first exam there too. All right. But other than that, I think that's kind of just a quick recap of what we did. I think that's all I need to chat with you guys about. I don't think anything else kind of comes to mind there, right? Anyway, so let's get started with prayer, and then we'll continue on here. But Lord, we just thank you for another day full of blessings. We thank you for another day that we can just turn to you whenever we want. We just thank you, Lord, for just listening to us and your desire to spend time with us too, Lord. Just help us to understand your heart. Help us to understand how you show your love for us, Lord, and that we can understand that and share that with others also. Lord, just give us an opportunity to share what you've done in our lives with somebody around us today, and give us the courage when we see that opportunity to step up, Lord. And we just ask all this in your name. Amen. All right. So, we had ended with this. And, geez, started losing my voice. All right. Sorry. Don't worry, I'm only recording me losing my voice. Cool. All right. So, if let's see if we can try this without croaking. If we have a molecular compound, right, that contains 2 or more elements, that's something that we kind of talked about in the first chapter. Let me see if I can turn off the lights here. Wrong ones. That's going to put you guys to sleep. Is that all right? Can you guys still see this stuff? Yeah. Okay, yeah, all right. And it'll be a little bit easier to close your eyes, right? So, right? On the nano scale, so if we could zoom in and take a look at our molecule, we would see there is a discrete thing, right? So that's what I'm just talking about when we're discussing the idea of a molecular compound, right? If we could have the world's best microscope and zoom all the way in on one particular thing, right? So we have a couple of different representations that we're going to learn. We're going to talk about how to draw things. We're going to talk about how the bonds are connected and all that kind of stuff. That's chapters 6 and 7 is where that's going to come in. 6, 7, and 8, I should say. Right? But we're also going to start by learning about what the molecular formula is. Now, I think, for the most part, everyone's had some familiarity with molecular formulas. Right? And so it tells us the elements that are used and how many there are. Okay? So we have this mysterious thing called water, and it's H2 and O, right? So it shouldn't be a huge shocker that it has 2 hydrogens and 1 oxygen as part of its discrete molecule. Okay? Pretty straightforward there, right? What we're going to get into is we're going to learn about the naming a little bit, and we're also going to learn about how to calculate those molecular formulas. Okay? So that's kind of where we're going next with all this. So how can we represent this? You guys, there's nothing here for you guys to really copy down. But there's a lot of different ways that we can represent these discrete molecules, and that's actually a very important thing in chemistry, right? So especially as we progress along to organic chemistry and biochem and all those kind of things, right? We're going to get into the idea of, oh yeah, if you guys run out of space, just fill in the blanks in between there, please. As we get into the different levels of chemistry, we're going to have to look at the shape quite a bit. Shape is going to be extremely important, is what it is. All right? And so again, we're going to get into that in chapter 6 and 7, so I just want to give you guys kind of a little preview here about what we're going to do in different ways that you guys can see things here, right? So this kind of spaghetti-looking stuff down there is the realm of biochemistry, right? When we look at these complex molecules that have hundreds or thousands of different atoms that are carbon, right? And so you guys will talk about proteins and those kind of things in there. But there are different representations that are in the book also, and so that's just kind of what we're showing here, okay? All right, so how do we start to get into naming of these things, right? So broadly speaking, there's 2 classes of compounds, okay? So when we go through and name things, I'm going to kind of give you guys let's say an importance tree, right? How can we walk through these different things? How can we start to identify molecules, that kind of thing? So the first kind of branch is that we have organic versus inorganic compounds. Okay? So one assessment we need to make, are we dealing with organic or inorganic compounds? Now, I'll go ahead and give you a hint. Okay? Are we in organic chemistry? No. So are we going to learn all the rules that come along from naming organic compounds? Not yet. Okay? So the first branch in our tree, they're looking at organic versus inorganic. We always have the same answer. Okay? Organic compounds are going to have a different naming scheme for those that we're not going to learn. Okay? So we're going to be sticking on the right-hand side here, the inorganic chemistry stuff. Sound good? Okay? What's the difference? The difference really just comes down to whether we have carbon there or not. Okay? Now, this isn't an exclusive, representation or list of things, right? What's the actual definition of an organic versus inorganic compound? Well, it depends on who you ask. Right? That's the honest truth with that, okay? So we'll discuss a little bit more later on, right? So organic compounds usually contain carbon and hydrogen. They may contain some other elements, right? And over here in the inorganic, we tend to have things that don't always have carbon as part of them. Does that mean we're never going to name something with carbon? Well, no, of course not, right? Right, so an example that we have coming up, we're going to name something called carbon dioxide, right? So that kind of lives in this in-between world in some people's eyes about whether it is or isn't organic or inorganic. The point being, we're always going to be sticking on the right-hand side here for us. And that has a certain set of rules that we're about to learn. Sound good? You guys with me on that one? So when you go through and naming something, inorganic naming is where we are. And then we're going to have another branch that comes out of that in just a second. Okay? Good. Thank you very much. Ooh, I get a free pen out of it also? All right. Well, I got somebody's pen up here, so. Yeah. All right. Couple of quick definitions here, things to think about. If we have something called ethanol, right? We have a formula that goes with it, C2H6O. Okay. Now, what we just discussed is that the formula tells us what elements are present, carbon, hydrogen, and oxygen, right? And how many there are, right? 2, 6, and 1 respectively. but it doesn't tell us anything about how they're actually connected to each other, okay? And the point being, we can actually connect those carbons, hydrogens, and oxygens in different ways. And these are both valid representations of how we can hook all those molecules together, okay? So just because we have a formula doesn't necessarily tell us exactly what we're dealing with, and that's why naming is important. Because we can have a formula, but if we give it a different name, such as ethanol, right, versus dimethyl ether, right, these have very different properties. And so when I'm talking to another scientist, another chemist, I can't just give them the formula, I need to tell them the name of something, or to draw it out would be even better, okay? Everybody following along with me on this? Okay. The idea here we have are constitutional isomers. Okay, we have the same formula, but they're connected differently. Okay, so when somebody says the word constitutional isomer, they have the same formula, C2H6O, right? But the way that those atoms are connected together are different. Okay. And there's a couple other red highlighted stuff here that we'll be discussing as we keep moving on here, right? Empirical formulas, structural formulas, Lewis structures, all that kind of stuff. Good? Looks like you guys are still copying things down, so we'll take a quick second. Alrighty. Okay, so here's that branching that I was telling you guys about. Up at the top, right, we have the choice between organic and inorganic. Okay. We're always going to be on the right-hand side there with the inorganic stuff, but we have a choice to make. The choice to make is whether we're dealing with covalent versus ionic compounds. Okay. And now this is coming back a little bit to what we discussed at the beginning of chapter 2 and even back into chapter 1 already. Okay? So what's the difference between a covalent and an ionic compound? A covalent compound has two nonmetals bound to each other. Okay? So two nonmetals bound to each other. Ionic compound is a nonmetal and a metal. Now, how in the world are we going to figure out whether something's a metal or a nonmetal? The periodic table, got it? So if you look back just a couple slides, there was a kind of color-coded periodic table that had the metals and the nonmetals, kind of, I think it was yellow and green is what they were, right? So that's the first thing that you guys need to do, identify where on the periodic table the different components that you have in your formula are. Are they covalent? Excuse me, are they metals or are they nonmetals? And that's going to tell us whether they're covalent or ionic. Okay? If we're under the covalent compounds, we only have one choice from there. They are invariant. Okay, and we'll talk about what we mean by variant in just a bit. Okay? They are invariant, and so we have a naming system to deal with invariant covalent compounds. Guys following along on that? Right? So we have invariant covalent compounds. That's what you guys are going to learn how to name. Okay? Carbon dioxide is carbon dioxide. There's no other way of naming it. Following the established rules, right? There are these kind of slang terms for them, right? These, let's say, colloquial terms sometimes, but those aren't the rules that we're following, right? We're following established rules. If you're under ionic compounds, you have a nonmetal and a metal. We have two choices. Are they variant or invariant? Now, we haven't talked about this, but let's see if you guys can figure it out. Okay? If we use the periodic table to assess whether we have a metal or a non-metal, what tool do you think we're going to use to assess whether something's variant or invariant?
Periodic table.
The periodic table. Okay? So this is all going to come from the same place. You guys with me on this? The location of the metal on the periodic table is going to help us with invariant versus variant. Got it? So we'll kind of point out where we're looking for things. We're looking for variant or invariant. Sound fair? Okay, is it important to recognize the periodic table? Yeah, right? Okay. And where does this come from? Well, we can have something known as iron 2 chloride versus iron 3 chloride. And there's a big distinction between those two, okay? One of them gives nice pretty colors, the other one's kind of dull and brownish, right? All these kind of things, right? One of them's nice green, light green there. So different properties, different structures, different reactivity, right? Different solubility, all this kind of stuff that comes with it. So we need to be very specific whether we're dealing with iron 2 versus iron 3. And we'll talk about how we actually get those Roman numeral things in there. That's going to be the variant or invariant part for us. Okay? And so each one of these branches in the tree have a separate naming rule for us. And we're going to start with the covalent compounds because they're a little bit more straightforward. Sound fair? All right. Okay, so here we have some things. So take a moment, look at things, and then assess things, right? We got nitrogen oxide. You could also call it nitrogen monoxide. That might be a fair name too. We have nitrogen dioxide, dinitrogen monoxide, dinitrogen trioxide, right? Okay. Dinitrogen tetroxide, dinitrogen pentoxide. You guys got the naming system? How is this going to work? We'll take a look at our formulas, right? So if we take a look at this one down here at the bottom, right? We've got N2O4. So my formula tells us that we have 2 nitrogens and 4 oxygens. Good. How do we represent the number of atoms, right, in our name? Well, if I've got 2 here, it looks like we use the prefix di. Got it? And then we put the name of our atom. We're dealing with nitrogen, right? So dinitrogen tells me I have 4 nitrogens. And I have a prefix of tetra, right? And I'm using oxygen. Now we're going to break this down in the next couple of slides. But when we're dealing with covalent compounds, the key thing to recognize, the key thing to deal with, is that we're going to use our prefixes to say how many of the atoms there are. Okay? That's one of the core differences between covalent and ionic naming. The di, the tri, the tetra, the penta, the hex, whatever it is, that tells us how many of the atoms there are present. Okay? Everybody following along with this? Just kind of looking at the pattern of how we name things and how we break that down. Good? Now what you'll notice is I don't call it dinitrogen tetraoxygen, right? I call it tetroxide, right? We have "ide" endings, these IDE endings at the end of the second element in our formula there. And we'll talk about that in just a second too. But everybody with me on this, kind of seeing the pattern of how we name things, right? Not too bad. Put the nitrogen, right? Put this element first with how many, put this element last with the appropriate prefix there. Good? Cool. So let's break all that down. Let's come up with our, let's say, rules to follow here. Okay. I'll give you guys a second to kind of read through this and copy it down, and I'll start talking through it with you here. So the bullet points that we have up there in the top half of the slide are the observations that we have from the previous examples. Right? Just kind of put in a nice condensed bulleted form. Those are important for you guys to recognize, important for you guys to understand. Okay. Okay, so a couple of thoughts here. So at the top there, we are going to be restricting the naming that we're learning. And what I mean is we're only going to be dealing with binary compounds, okay? So at most, you're only ever going to have 2 elements together with something that you guys need to name, okay? Well, that's fairly restrictive, but the reason why we do that is because as soon as we move past 2 compounds, or 2 elements, the naming rules change, actually, is what it is. And so we'll have to learn a little bit more before we come back and kind of start to name more complex things. But don't worry, we'll get there, right? What I'm saying is it gets worse. Sound good? Okay, good, all right. We're starting with this simple and we'll work our way up. That's all I'm saying, all right? So we're only ever going to be having 2 elements in there that we have to name. That's what we mean by binary compound, okay? We name the elements in the order they appear in our chemical formula, all right? Now, we're not going to talk about that so much here, but there are some conventions for how we should order the elements in a chemical formula, okay? So typically we order them based off of atomic weight, although there are some exceptions to that also, okay? We'll work through some examples and it'll start to become a little bit evident what we do. Prefixes show the number of atoms present. These are the prefixes here, okay? So most of these should be probably familiar with you guys as we've seen these prefixes in other places, right? Mono, di, tri, tetra, penta, hexa. Hepta is kind of the weird one maybe. You guys might be used for, might be used to seeing sept, right, is another prefix that you sometimes see for 7 or something, right? Octa, nona, and deca, right? Do I expect you guys to know those prefixes? Yes, okay? But like I said, most of those are kind of self-evident, right? We've drawn, pentagons and hexagons and heptagons, right? These geometric shapes where we're familiar with the number of sides that come with them, right? So same idea here. Each element is considered invariant. Okay, so this is important, and it's not as overtly evident what I mean with that now, but as soon as I show you what an invariant element is, then that should help clarify that, right? Variant elements are going to change how many things they can bond to based off of the charge that they possess, okay? So we're going to talk about charges and that kind of stuff in just a little bit. But what I mean is, while we're dealing with covalent compounds, we consider everything invariant, okay? We change the ending of the last element to IBE, right? We keep it stem, and we just add the IBE to the end of it, okay? And then this is for nonmetals bound to nonmetals, our definition of a covalent compound. Everybody got that down, right? So I walk you guys through a quick example here. If I ask you what's the name of CO2, right? A very typical question. The first thing you ask yourself is this a covalent, right, or inorganic compound? Right? And how do we answer that question? Is this covalent or is this inorganic? You guys would look to the periodic table, right? So if we tab ourselves over there real quick. There we go. Right? We got our buddy, right? We're looking at CO2, right? There's carbon, there's oxygen, right? They're on the right-hand side of the periodic table. That means they are nonmetals, right? So we have a nonmetal bound to another nonmetal. So that makes this a covalent compound. Therefore, we are in that branch, right? We are in that tree in our minds when we go to name these things. Sound good? That's the first question asked, right? If you skip that step, then you're going to name it in the wrong way, okay? So there we go, right? So step number 2, right? We have to figure out how many of each of the elements that we have, right? So I'll just color code this in purple here just to kind of separate things out. We have 1 carbon. I'm going to ask the obvious question. Does everybody see that I only have 1 carbon? Okay, good. So your eyes are working today. That's excellent, okay? So, now if you take a look at the rules that we had on the previous slide there, right? It says that we have to use the prefixes, right? We have to use the prefixes to be able to name this. Sound good? So would we call this monocarbon dioxide? No. Maybe, right? Is that what the rules are telling us so far? Yeah, they are, aren't they? Right? So let's leave that written down here for just a second, okay? Because look, I'm just right. Just don't let me tab back here for a second. Okay. Point number 2: prefixes show the number of atoms present. That's the rule that I'm following. We have 1 carbon. You guys all agreed with me, right? And the rule says, put that in there, right? You guys look suspicious. I don't know, okay? Okay. Now what else do the rules say? Okay, so the elements go in order. We use the prefixes to denote how many there are. The second part of it, we take the stem, right, and we add the IDE to it. Now this is going to be the one tricky part that only comes through practice. Okay, what is the stem for all the different elements that we have, right? It may or may not be so obvious that the stem for oxygen is ox, right? What is the stem for fluorine? Right? So typically, right, if we just think about this for just a second, okay, the INE endings, so fluorine, chlorine, bromine, iodine, right? We typically drop those INE endings, and that the rest of it is our stem. Is everybody following along what I'm trying to point out here, right? So we have to be familiar with what the stems are, otherwise you're not going to name it properly. Got it? The real easy way to do that is just do some practice. Now you guys are all going to be practicing this anyway. Right? Okay. Okay? That's the only way to really get comfortable with this. There is no Gnostic wisdom that I'm withholding from you. Right? I'm not hiding some secret in my pocket that says, oh, if they only knew this, then they wouldn't have to practice. Okay? It's just practice. That's what it comes down to. So getting comfortable with your stems and that kind of thing. Okay? So the INE endings or the GEN endings, nitrogen, right? Those are usually omitted, and the stem is whatever is left over. And don't worry, we got plenty of examples coming up, but I'm just trying to talk you guys through it for the moment. Sound fair? So knowing the names of your periodic table, right, and the INE endings versus the GEN, those kind of things, right? Those are typically what's dropped and the stems are left over. Okay? So for oxygen, we have ox, and it tells us to put the IDE ending, right? And how many do we have? 2. Got it? So dioxide. So our name of monocarbon dioxide. Is that a correct name based off of the rules that we have established? Yes. So if you put that down on an exam or a quiz, would you get it right? Yeah, right? I'm not going to lie to you guys, right? There's the rules, follow it. Now we do have a couple of conventions that we have to deal with, right? And I think that's on the next slide. But everybody following along with this. We name the things in the order that they appear in the formula, and we use our prefixes to say how many there are. And for the thing at the end, we add the IDE and keep it stem. Those are the rules. Sound good? Pretty straightforward, right? The only tricky part is remembering what the stems are. All right, let's tab back over here. There it is, right? And I kind of just, that's what I was breaking down there for you guys on the other slide. All right. Aha. Up at the top there. Typically, okay, by convention, if you want to say that, the mono is optional for the first element. What does it mean to be optional? Can you leave it in? Sure. Can you omit it? Sure. Which one's better? The one that takes less calories, right? Do you know how many calories it takes to write mono for something? It's like upwards of 1/10 of a calorie. Oh, I can't afford that, okay? But hey, look, the secret is not everyone can get to the gym, right? So you got to get them gains while you can, right? Burn them calories by writing out mono, and then you're going to get swole in chemistry class. All right, so you guys with me though? So does it matter? No, either way you guys want to do it is just fine. That's why typically, or you've probably never heard monocarbon dioxide, right? Everybody just refers to it as carbon dioxide. Sound good? Cool. So a couple of things to practice here also. I gave you guys the name of things, right? So if you want to just cover up this side, when you're at home, you can practice naming those. See if you can go back and forth between the name and the formula and the name, right? This is a two-way street. If I give you one bit of information, you guys should be able to give me the other. If I say SF6, you guys should be able to say sulfur hexafluoride. If I write out sulfur hexafluoride, you should be able to get SF6 from that. Sound good? So a couple of things just to look at here. So diphosphorus pentoxide, right? The IUPAC discourages contracted names, pentoxide and decoxide. Okay, what the heck does that mean for us? So there's a group of nerds who get together right? And they write big books that say, here's how we name things. That's what the IUPAC is, the International Union of Pure and Applied Chemistry, okay? And they get together and say, here are the rules for how we name these things. Got it? Now, I joke about it, but is that important? Oh yeah, it is, right? Because if we're doing chemistry in the United States, we can't be doing different rules than what's going on in Brazil or Canada or something like that, right? The scientific community is worldwide, so we all have to be working through the same rules. So that's who we're following, and those are the set of rules that you guys are learning. So if you ever see something called the IUPAC naming, that's where it comes from, right? A bunch of guys got together, and that's what they came up with, and here we are. Sound fair? Okay. All right. So, but it says they discourage it. I don't think there's any of them in this room, right? Any of you guys work for the IUPAC on the weekends? You do? No, okay, I guess we have to follow the rules then, guys, right? You guys with me on this? So if you're on an exam and you put pentoxide instead of pentaoxide, I'm okay with that, okay? The weird part comes from just how we pronounce things in English, right? An A next to an O, right? The syllables there might make different sounds, right? That's kind of what they're trying to avoid. What does that mean for you guys? Don't worry about it, but I'm just giving you guys some of the exceptions here. Okay? Got it. I think we got some practice coming up in a little bit too, so. But first, okay? Wait a minute. Oh, my titles are just, I apologize about that. Sorry, I'm like, wait a minute, that's not the right. So binary, inorganic, okay, never mind, I'm confusing myself. Excuse me. So, what are some exceptions here? When we have group 6A and 7A nonmetals plus a hydrogen. Okay, so first of all, what do we mean by 6A and 7A? Now, how do we start out naming anything for this class? We look at what first? Periodic table, okay? So if you're taking a look at the periodic table, and don't worry, I'm going to pop back over here in just a second, okay? But if we take a look at the periodic table, if you see things like 6A, 7A, that kind of stuff, right? They're referring to which family in the periodic table you guys are, the elements are. So let me just get this out of the way, right? So some periodic tables have them labeled with 6A and 7A, some of them don't. This is our sixth family there, so oxygen and sulfur, selenium, tellurium, right? That's 6, and this is 7, okay? You guys with me on that? So oxygen down, and fluorine down. So if any of those atoms are bound to a hydrogen, we have a subtly different way of naming it. Okay, so very specific conditions. One of those elements, and it's bound to hydrogen. Good? Everyone follow along with that, right? So what do we do if that's the case? Okay. So we omit all of our prefixes. So if we have hydrogen bound to any 6A or 7A. Sometimes you might hear it referred to as group 16 or group 17. Depends on what well, who's got their book with it? Can I peek in your front cover here real quick? I think the book has the, yep. So if you take a look at the front cover for your textbook, they've got the 6A and 7A labeled in there, okay? So, there it is. Good. So what are the consequences of this? So we have hydrogen and chlorine. Hydrogen bound to a group 7A metal. We follow all the naming rules, but just omit the prefixes. Right? So we have chloride. Right? We have the stem of chlorine and the IDE ending that we add to it. So hydrogen chloride. Not monohydrogen monochloride. Just hydrogen chloride. Good? Everybody following along with that, right? So down here at the bottom, So some of you guys might have seen there's these websites that pop up, or people are walking on the street and they're like, do you want to ban dihydrogen monoxide, right? They laugh at it because people don't know how to name things in chemistry for some reason. Right? Well, wait a minute, I know what, okay, that sounded bad. What I meant is they're trying to get gotchas on people just because they don't remember their naming rules in chemistry, as if that proves anything, right? So I don't understand that is all I'm saying, right? But anyway, if we follow the naming rules for H2 and O, we would call it dihydrogen monoxide. And that's supposed to sound scary or something, but of course we just call that water is what it is, right? So we have a couple of common words that are common terms that we use also. Ammonia, NH3, okay? So we call it nitrogen trihydride or something like that, right? Practically we would never call it that, we would call it ammonia. Now I like ammonia, and the reason why is because it reminds me of one of the funniest stories I ever read about an exploding Slim Jim factory, okay? Right, that's the only thing you can do when you hear about that, right? Just imagine Slim Jims just flying through the air for miles. So this is when I was in school in North Carolina, and now the question in your mind is like, hey, wait a minute, why are they using ammonia to make Slim Jims, right? Well, if you've ever eaten a Slim Jim, right, then you probably know that's what they taste like. I'm kidding, right? I'm gonna get dropped by my sponsorship from Slim Jims, oh no. Right? But no, that's not the case. Ammonia is used a lot, actually, in industrial settings. It has some very unique properties, not too far away from how water behaves, right? And so it's used a lot in cooling applications, right, to cool things down on the industrial scale, right? So they weren't using ammonia to make the Slim Jims or anything, right? They were using it as part of the cooling process. And then something went wrong, and things exploded, and Slim Jims flew across the area there, okay? But we're going to spend a lot of time talking about water. That's going to be one of the big things that we discuss quite a bit throughout the semester. And then we're going to, always in the back of our minds, we're going to have kind of ammonia's very similar properties to it. And we'll learn why in chapter 7, okay? But anyway, aside from Slim Jims and all that kind of stuff, so we have a couple of exceptions for the naming. If it's outside of these exceptions, we're following the rules. Sound fair? Right? So just know the rules, do a little bit of practice. You had a question back there.
So if we had one of these on our test, should we memorize the names, or should we, like, would we get it correct if we did it the normal way?
So these are the established rules for naming these, right? So this isn't just a suggested exception, like when we dropped a mono or something like that. This is the correct naming system for these setups, right? So these are exceptions that you should know, right? So if you're 6A and you're 7A and you're bound to hydrogen, that's the rules that we follow. Right, the only thing you do is just drop the prefixes for it, right? What's up?
Are these the only 6 common names that we need to
No, there are other ones, but these are the ones that we might run into quite a bit during this. I don't need you guys to memorize those names. I think you guys should know water. Right? I think I had to go ahead and put that in your back pocket there to keep around, right? But ammonia, I'm not going to expect you guys to know that. It's just in case I am talking about it or something like that. I don't need. Most of the time when the question is, should I memorize this stuff, especially just kind of like trivia knowledge like this, right? The answer is mostly going to be no, right? This is an opinion, right? There's no value in you guys being able to pull out phosphine and the formula for that just because you memorized it, right? I'd rather you guys understand how to draw phosphine, or what properties it has, or how we can use it, how we can apply it, how it reacts. That has value with it, right? But just memorizing its name, not going to be too interesting for us. Does that sound fair though, right? So, but feel free to ask. I'll be happy to clarify. Like, hey, should I memorize this kind of stuff, right? But for the most part, the answer is going to be no with that. Hydrazine is cool, right? That's rocket fuel. So, just giving you guys lots of good ideas on what to do over the weekend here, right? All right. So good. That is the end of naming covalent compounds. That's all there is to it. You follow the order and the formula, and you use your prefixes to say how many there are, and you do the IDE ending. Nice, easy, simple. Those are the ones that you guys are going to like. Now we're going to do the ones you guys don't like as much. Okay? These are the ionic compounds. Now the ionic compounds are going to be the ones that we're probably going to spend the most time on. We're going to talk about a lot of their properties. Okay? Not just in this chapter is what I mean. Okay, so first of all, let's get some terms here. If we're dealing with an ion, we have charged units, right? They're formed by the transfer of electron between elements. Now, we could go back and say, all right, how do we define an element? And you guys would say elements are defined by the number of protons. Got it? If we're dealing with a neutral element, okay, then the number of protons is equal to the number of electrons. And if you remember, I said that for our purposes, from now pretty much all the way through biochemistry, chemistry happens by the movement of electrons. So having electrons hop in between different elements, make bonds, break bonds, transfer electrons, that's going to be what we're going to be studying. Okay? And one thing that happens as we transfer electrons is that we form ions. Okay? We have two types of ions. We have cations and we have anions. So cations and anions. Cations if we have something positive, anions if we have something negative. We're going to have to identify what is positive and what is negative when we go through and name things. Okay? So we're going to have to identify what has a plus and what has a minus. We're also going to have to identify how much of a plus and how much of a minus. And this is where we're going to get to the variant versus invariant part. Okay? Like I said, I'll cover this stuff again, but I'm just trying to condense everything down quickly, right? The variant and invariant refers to what charge can something have. Some elements only have very specific charges. Those are invariant, okay? Some elements can have multiple charges depending on what they're bound to, and those are going to be variant. So how in the world are we going to figure all that out? Well, we're going to use one of the rules of nature, okay? The ways that the universe works. The way the universe works is that there always has to be a balance, right? That's why George Lucas made Star Wars, right? That was his inspiration. His inspiration was chemistry. Don't look it up, it's true, okay? 100% true, right? You guys seen Star Wars movies, right? The Force, the good, the bad, the light, the dark, right? Everything has to have a balance. What do I mean by this? That means if I have a cation, I have to have an anion. Good? Let's say I have a cation that has a +3 charge. What do I need to have? Enough anions to balance that out. Okay? If I have the plus, I have the minus. If I have the light, I have the dark. If I have the good, I have the bad. Everybody with me on that? And that's the math that we're going to use to figure out how much of a charge something has. Good? So the math is adding things up and making it equal to 0. Nice, I like it. Seems straightforward, right? Now, question. How can we start to know what the charges are on different compounds? And from there, we're going to have to use something called a, let me check my notes here real quick. What's it called? A periodic tablet? Oh, a periodic table. Sorry. You guys with me? Okay? It comes from the periodic table. You guys saw that. Right? It comes from the periodic table. All this stuff comes from the periodic table. This is another thing we can read off of that. Okay? How important is the periodic table? Very. Okay? So, real quick, how do we know how many electrons something gains or loses? Well, they want to get to their nearest noble gas configuration. That's going to be the short answer that we work with right now. Okay? Does that make sense? Everybody got that? 100%? Don't need to talk about it? Yeah, okay, good, right? Okay, moving on now. So what are we talking about with this? Where are the noble gases? Well, the noble gases are on the far right-hand side of the periodic table. Helium, neon, and all the other ones that are in that family there. Those are called our noble gases. Why are they called noble gases? Well, they're a gas, and they behave like a noble, right? Very regal. Don't like to mix with the common folk. Like us professors. That's why I stand at the front. right? I don't want to be I'm kidding, right? Right? But that's what they thought about. When they first discovered noble gases, they weren't very reactive, right? So they considered them noble, right? They didn't want to mix with other things, all that kind of stuff, right? The aristocracy, right? The ones that are better than everyone else, right? So that's why they just call them noble gases. In reality, that's not true. Noble gases can react with quite a few different things, right? And so we might see some oddball noble gases kind of making some cool compounds that we look at later on in this semester, okay? But so the name just comes from antiquity when they first discovered it, okay? So if you take a look on the right-hand side of your periodic table, they are group 18 or group 8A. Yeah, what's up?
For the metalloids, would they be filed under cations or anions?
Right, a very good question, right? So the question was, well, what happens with the metalloids? And the answer is it's going to depend on what they're bound to, right? So those are a little bit tricky. That's they live in both worlds, right? So we'll talk a little bit about those and then we'll see how we can assess them, right? But a very good question, okay? So, noble gases, right? Let me just pop over here again. Put it in, and there we are. Here we go, right? So all these on the right-hand side, okay? Now, we're going to learn something along the way. I'm going to teach you guys something that's called a rule, but it's a bullcrap rule, okay? I'm making it up, like pretty much everything I teach you guys, right? I don't prepare when I come here. I'm just like, I hope nobody actually calls me out, right? Good, no one's called me out. All right, good, so I can just keep going, right? But what I'm saying is I'm going to teach you guys a rule. And as with most rules in chemistry, its function is there to save us time, okay? Are there going to be exceptions to these rules? Yeah. Will I talk to you guys about them as we go through and kind of introduce them? Absolutely, okay? But most of the time, if we want the actual answer, we have to do some really complicated math that involves some integrals and graphing things and all that. Does anybody want to do some integrals real quick? Me neither. Good. All right, so we're going to follow these kind of simple rules, but you have to understand that whenever we take shortcuts, we leave things off, right? But we have to make sure that we understand that as we go through these things, okay? So we'll talk about octet rules, okay? And what I'll tell you guys later is that the octet rule, right, has its time and its place, but there are some problems that come along with it too, okay? But there are noble gases off on the right-hand side. All right. Oops, that's chapter 1. And then we can go back to chapter 1 if you guys want. How's that sound? Good? No? Okay, we'll keep going. All right, learn new things, okay? So what I'm saying is this. So if we're in our main group, right, our non-metals kind of over there on the right-hand side, that kind of thing, right? Well, I should be careful. I need to be very specific here. For most elements, let's leave it like that for the moment. For most elements, they want to get to the noble gas in the least amount of steps possible, okay? So it's like this. If I say, I will give you guys 50 points of extra credit, okay? I'm not that nice, right? Okay? I will give you guys 50 points of extra credit, and you have two ways of doing that. Your two ways of getting the 50 points of extra credit is run 5 miles or run 2 miles. And either one you do, you'll get the same credit. What are you guys going to pick? Like, well, I don't like to work out, so no extra credit for me, right? Right? Which one do you take? Run 5 miles or run 2 miles? Look at all you lazy people. What's wrong with you, right? Don't you want to stay fit, right? You guys get the point I'm making? Take the least amount of steps to get there, right? So I said this to my organic chemistry class, and I'll say the same thing to you. You guys are made out of elements, okay? You guys aren't shocked, that's good. Elements make up molecules, you're made up of molecules. All elements and molecules are lazy. Therefore, if somebody calls you lazy, you're like, well, I'm just made of elements, right? What can I do about it, right? What I mean is this, they will always try to get to the lowest energy state. This is kind of the terminology that I will talk to you guys about. The least amount of steps to get somewhere, right? The low energy state, the ground state. These are the kind of terms that we'll start to throw around as we go through this semester, okay? Bringing it back up, all we're saying at the moment is take the least amount of steps to get to the nearest noble gas. Run the 2 miles instead of run the 5. Sound fair? Everybody following along with that? Cool. So, in brief, here we are at nitrogen. Its nearest noble gas is over here at neon. So, how many steps does it take to get from nitrogen to neon? Well, we've got 7, 8, 9, 10. Right, so it takes what? 3 steps to get there. Which way are we going on the periodic table? To the right or to the left? We're going to the... Okay. Do we have to gain electrons or do we have to lose electrons to get there? Gain, right? We're going from 7 to 10, right? So what charge would we expect nitrogen to typically have? We expect it to gain electrons, 3 of them, to get to the nearest noble gas. So what charge would we typically expect to see on nitrogen?
-3.
That's all there is. Got it? So looking at the periodic table, looking at how many electrons it begins with, how many steps it takes to get to the nearest noble gas, and then figuring out whether we gained or lost electrons, right? So how many must we gain or lose to get there? Fair? All right, I think we got some examples coming up here. Okay, see what you guys come up with. So figure out what charge would we typically expect these to have, okay? What charge would we typically expect these to have? Yeah.
I have a question. All the way down, right before the last.
For which group?
For the group, for the A,
Yeah, so there's 2 ways.
7, but
Yeah, so there's 2 ways that we have of kind of classifying the periodic table. I forget exactly what the 2 ways are, but they just come from how people used to organize this stuff is what it is. So sometimes you'll see it instead of 6A, you'll see it as 16, right? So that's not as important as just kind of recognizing which part it is. And very soon I'll get into a way that I will show you guys how to label the periodic table. Yeah, but if you take a look at the front cover there, you'll see it's labeled both ways in there, so you can use either one for that is what it is. I think the one that you guys have on the exam uses 16 and 17 instead of 6A and 7A, but, yeah. Hello? No, that's fine. I'm just peeking over your shoulder, making people nervous, as I tend to do. So what charge would we expect to see on these here? Would you rather than 5 cells or would you rather than 2 cells? Let's say yes for that. But it sounds like you weren't taking the right approach. You say, hey, wait, I think it'll be a fraction. Right, so you're starting here and you're gonna end up here, right? Make sense? You'll definitely need one of your tables here. Oh, there it is, yeah, the next slide. Right. So what are you telling me being the electrons, right? So what charge is that? So that's what I'm saying. It's a 2 minus, 3 minus, 2 plus, that kind of thing, right? We're still debating, guys, so bear in mind. What's that?
Ready?
How many do you where you starting? Starting at 38, right, and where do you start? Start off in the other place, so how many do you want? It's gonna charge you. There you go. Yeah. All right, looks like we're all getting the answers there. Good. Uh-oh, you all right? You what? Oh, no. +1, +2, -1, -2, that kind of thing. Cool. All right, I'm seeing a lot of correct answers, which means you guys are very, very smart, so I get to ask super hard questions on exams. All right. That's just the way it works, right?
No.
Good answer. All right, so if we're here, right, the first question was for sulfur. Right, so there's sulfur right there. Okay. We need to figure out how many steps to take to get to the nearest noble gas. Remember, your noble gases are over here on the right-hand side. Okay. So we start out at 16. Our nearest noble gas is over here in argon. Right? How many steps does it take to get there? One step to get here and another step to get there. Right? Are we adding or removing electrons moving to the right? We are adding electrons. So sulfur typically has a charge of 2-. Got it? Fair? All right. Next one. It's sodium. Sodium's over here. Right? So I'll do 1 step to get here, 2 steps to get here, 3, 4, 5, oh my gosh, 6, 7. Okay, 7, right? So sodium 7-.
No.
No. Aha, right? So if we start out at 11, the closest one is actually back here at 10. So would you guys rather run 7 miles or run 1 mile? Got it? So typically, we're going to have to look left or right. Okay? So if we started out number 10, started out number 11 and we end up at number 10, we lose an electron, we have a +1 charge with that. Sound good? Don't forget, left or right. Let me just erase that nonsense. Okay. All right, we had phosphorus. What did you guys get for phosphorus? 3-, okay? So we're right here on phosphorus. We can hop over, 3- makes sense. And then our good old buddy SR, which stands for? Strontium, very good, okay. Here's strontium right down here. What's strontium gonna do? 2+, right? So we're gonna walk backwards from 38 to 37 to 36 right there. Good? That's all there is to it for now. Bum, 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 right? What's up?
What about group 14 where it could be like,
Well, you'll notice I didn't give you a question out of that. But that is a very, very good question. What if we're at something like carbon? If we're at carbon, can we gain 4 electrons? Yep. Can we lose 4 electrons? Would you guys rather run 4 miles or run 4 miles? That's the question there. So the answer is we have to learn another tool along the way to kind of help figure that out, right? And there's going to be something important that we're going to have to learn along the way with that. But immediately our answer is we should classify things as metals versus nonmetals. And if you go back in chapter 1, was it chapter 1? No, I think it was in chapter 2 where I first introduced metals versus nonmetals. I said that nonmetals typically gain electrons, right? And metals lose electrons. So that might be the answer that we have at the moment there. But very good question, very good observation. Good? Everybody feel comfortable with this? All right. Let's see here. So let's mix in something from the previous work. Give me how many electrons and protons these things have. How many protons and electrons do these ions have? Okay. there's our buddy aluminum right there. How many protons does aluminum have? When is it not going to have 13? Never. Got it? That's what defines aluminum. How many electrons does aluminum 3 plus have? 10. Now, some of you guys might be saying, well, geez, Dr. H, this seems so rudimentary. Why are you telling us this? One of the ways I kind of pick questions, especially the ones that we work in class, is because I see these kind of mistakes happen over and over, okay? Because what we're doing, okay, so take a look at number 3 down there with fluorine, right? That's F with a negative charge. What happens sometimes is we are adding something negative. And that kind of sometimes sits a little bit oddly in our minds. Because typically we think about negative things as losing something, right? So sometimes the math gets mixed up with how many protons versus electrons we have. We are adding something negative, okay? Fluorine starts out with 9 electrons. If we add an electron to it, if we add something negative, it gains a negative charge. Okay? So just be careful when you're walking through your math with this stuff. I've seen, this is usually one of the easy questions on the exams. You know, tell me how many protons and electrons. And then students are kind of nervous on exams and they kind of rush through it maybe and they add up their stuff incorrectly there. Okay? All I'm saying is just stop, take 10 deep breaths and count your electrons. Good advice for life, right? For my life. Everybody with me on that? Sound good? Feel comfortable? All right, I think that's a good place to end for today. You guys get a whole extra 2 minutes of your life then, right? All right. I will see you guys on Monday. Don't forget about the quiz, please.